Section 9.1 Part 2, Estimating a Population Proportion. Lesson objectives. Construct a confidence interval for population proportion. Interpret a confidence interval for a population proportion. Recall, a point estimate is an unbiased estimator of the parameter. The point estimate of the population proportion is p hat, which equals x divided by n, where x is the number of individuals in the sample with the specified characteristic and n is the sample size. Let's do an example. In 2008, a university poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. The number 1,123 were in favor. Obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So the solution, p hat is x over n. So if we take 1,123, the number of people who are in favor, and divide it by the total number, we get 0.63. Lesson objective. A confidence interval for an unknown parameter consists of an interval of numbers based upon a point estimate. The level of confidence represents the expected proportion or percentage of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted 1 minus alpha times 100%. Basically, all we need to know is for this class we're going to use three levels of confidence: 90%, 95%, and 99%. As we increase the level of confidence, our confidence interval is going to get wider. So it's a balancing act to pick the highest level of confidence and at the same time minimize the width of the confidence interval. Confidence interval estimates for population proportion are in the form point estimate plus or minus margin of error. The margin of error of a confidence interval estimate of a parameter is a measure of how accurate the point estimate is. The smaller the margin of error, the better the confidence interval. So if we look at this visual, here's our point estimate. This is our best guess for the parameter, and it's always in the middle of our confidence interval. And if we subtract the point estimate minus the margin of error, we get our lower limit. If we add it, we get our upper limit. So what can affect how big the margin of error is? Well, the margin of error depends upon three factors. Level of confidence is the first one. As the level of confidence increases, the margin of error also increases. The sample size. As the size of the random sample increases, the margin of error decreases. It gets smaller. And the standard deviation of the population. The more spread there is in the population, the wider our interval will be for a given level of confidence. So it's a balancing act. We want highest level of confidence, but at the same time as we increase it, the margin of error also increases. The sample size, as we increase the sample size, the margin of error decreases, but as the sample size increases, so does the time and the money to collect the sample. So it's a give and take. These two we can control. Number three, we don't have any control over. So the question becomes, how do we compute the margin of error? Well, before we can answer that question, we must talk about the distribution of p hat. So the sampling distribution of p hat. For a simple random size n, the sampling distribution of p hat is approximately normal with mean mu of p hat, so this is the average of all the p hats, that will equal the population proportion, and the standard deviation is given by the standard error of p hat, which is the square root of p times 1 minus p divided by n. And this is true that n times p times 1 minus p has to be greater than or equal to 10. So this is sort of like the requirement for the central limit theorem, where n had to be greater than or equal to 30. In this case, n times p times 1 minus p has to be greater than or equal to 10. We also must require that each trial be independent when we're sampling from finite populations. But there's only one problem with this. We don't know p, and that's why we're using p hat to estimate p. So what we're going to do is we're going to use p hat here in case of p. So when we look at our formula for confidence intervals, it looks like this. Our lower bound is p hat minus z alpha over 2 times the standard error, where that's equal to p hat times 1 minus p hat divided by n. The upper bound is our point estimate p hat plus z alpha over 2 times our standard error. Now what is this z alpha over 2? Well, this is what we call the critical value of z, and it is determined by the confidence level. Now we must note there's two restrictions here. N times p hat times 1 minus p hat has to be greater than or equal to 10 for it to be normal, and the sample size must be less than or equal to 5% of the population. So let's look at the critical values of z. If our level of confidence is 90%, z alpha over 2 is 1.645. If our level of confidence is 95, it becomes 1.96, and if it's 99, it's 2.575. So as we increase the level of confidence, the critical value of z alpha over 2 increases, thus our margin of error increases. So the general form for a confidence interval for a population proportion is point estimate plus or minus margin of error, which is the same thing as our sample proportion plus or minus our critical z-score times the standard error. And in symbols, that would be p hat plus or minus z alpha over 2 times our standard error. Another way of writing confidence intervals is by using capital letter E, which represents our margin of error, z alpha over 2 times our standard error. Now if you ever see Q, Q is the same thing as 1 minus P. And if we look at it, there's actually three ways we can write a confidence interval. We can say p hat minus E is our lower bound, p hat plus E is our upper bound. So we can write it as an inequality. We can write it as a point estimate plus or minus a margin of error, and we can write it in interval notation, lower bound, comma, upper bound. Thanks for watching.